Hello. In this video, I'm going to show you the formal mathematical definition of a limit and try to explain how that definition works. Here's what it looks like. Here's a quick look at this definition, and you'll sometimes see it referred to as the delta-epsilon definition of a limit because it has the Greek letters delta and epsilon playing a big role in this definition. So I'm going to be trying to explain what this definition actually says and how it works in this video. But before I do that, let me talk a little bit about, is it really important to know about this? And well, that depends on who you are and what you're studying. If you take a beginning high school or college level calculus class, your teacher might never even mention this. You might never see it or hear about it. Or your teacher might spend a lot of time on it and do a lot with it and require you to understand it and do proofs with it and things like that. Or, more likely, probably somewhere in between. When I first studied calculus in high school, I had a teacher who really liked the theoretical side of math. And he taught calculus from a very theoretical, pure math standpoint, with lots of theorems and proofs and mathematical definitions like this one. So in that class, we did spend a lot of time with this delta-epsilon limit definition, using it and proving things with it and so forth. Now that's kind of an unusual way to teach calculus at that beginning level. It's not the way I would do it. When I've taught calculus, I have not spent anywhere near that much time on this definition. I've basically just said as much about it to my calculus classes as I'm going to say to you in this video. Basically, I think that if you're studying calculus for the first time, you ought to at least see this definition, but I wouldn't require you to really understand it or work with it. So at that level, I would just basically show you, okay, here's the definition, here's a little bit of an explanation of how it works, and then as far as requiring you to understand it or do things with it, there might just be a bonus question or two on homework or on a test. So this is the kind of thing that if you were to go on and study mathematics at a higher level, you would eventually have to deal with this kind of thing. On the other hand, if you were, say, going into engineering, where you needed to be able to use calculus, but not necessarily to understand the theory behind it, you might never need to study this sort of thing. So in this video, I'm hoping to give you a taste. I hope you find it interesting, gives you an idea for how a mathematician would deal with this kind of thing. Now, before I explain the definition itself, some preliminaries, some warm-up exercises. So let's play a really dumb game. The way this game works is we each pick a number, and whoever comes closest to 10 wins. So I'll pick a number, you pick a number, and whichever one of us gets closest to 10 is the winner of this dumb little game. Okay? So my number that I picked was 10. So whatever you pick, the best that you can do is to tie with me. You can't get any closer to 10 than 10 itself. So if you picked anything other than 10, I win. I'm closer to 10 than you are. And if you pick 10, well, it's a tie. Okay, really dumb game number 2. This time the rule is you can't pick 10. You have to pick some number other than 10. So again, whoever comes closest to 10 wins. So each pick a number, can't pick 10, but whoever picks a number closest to 10 is the winner. Now, if you let me go first, you can always win, because whatever number I pick, you can always pick a number that's closer to 10 than the one I picked. So if I pick 10.1, you can pick something that's between 10 and 10.1, like 10.05 or 10.01. If I pick 10.01, you could pick 10.001. That's closer to 10 than 10.01 is. If I went low, picked a number that was a little bit less than 10, like 9.9, you can still find something that's between that and 10, like 9.95 or 9.99. If I pick 9.99, you could pick 9.999. So between any two real numbers, you can always find more numbers between them. So whatever I pick, you can always find something between my pick and 10, and you can be closer to 10 than I am. So there's no such thing as a number that's closer to 10 than any other number unless you count 10 itself. So how do we measure closeness to 10? Is there a formula that we can write where you can plug in a number and the formula spits out a measurement of how close that number is to 10? Well, how about if we just subtract? Take that number minus 10, the difference between that number and 10, and that'll measure how far that number is away from 10 itself, the difference between that number and 10. So if x is 10.1, x minus 10 would be 0.1. So that's how far 10.1 is away from 10. If x is 10.01, then x minus 10 would be 0.01. That's how far that number is away from 10. If x is something less than 10, like 9.9, then x minus 10 is going to come out negative. Like 9.9 minus 10 is negative 0.1. If x is 9.99, then x minus 10 is negative 0.01. So if we just take x minus 10, then if x is bigger than 10, we get a positive number. If x is smaller than 10, we get a negative number. What if that's not what we want? What if we only care about how far that number is from 10 in either direction without worrying about whether it's bigger than 10 or smaller than 10? So we want our distances from 10 to all be positive numbers. Well, to accomplish that, we can just take the absolute value of x minus 10. And that way, it's always going to give us a positive number that tells us how far away x is from 10. The distance between 9.99 and 10 itself is 0.01. That's how far apart those two numbers are from one another. So that's our formula for how close x is from 10. It's the absolute value of x minus 10. And in general, the absolute value of a minus b measures the distance between a and b. It's how close together a and b are. So if the absolute value of a minus b is small, that means a and b are close together. The distance between a and b is whatever that small number is. The smallest it could possibly be is 0. And in that case, that's when a and b are equal to one another. They're the same number, so there is no distance at all between them. So if the absolute value of x minus 10 is less than 2, that would mean that the distance between x and 10 is less than 2. That is, x is within 2 units of 10. X is a number close to 10. It's less than 2 units away in either direction. So it's between 10 minus 2 and 10 plus 2. That is, it's between 8 and 12. Okay, one more really dumb game. The way this game works is we each pick a number and plug it into this formula here. We plug it in for x into the formula x squared plus 4x minus 21 divided by x minus 3. And again, whatever value comes out, we're trying to get as close to 10 as we can. Whoever gets a value closest to 10 wins. If you want, pause the video for a second and play around with this formula. Plug in some different numbers and see how close you can get to a value of 10 coming out. So now I'm going to show you what's going on with this formula. The graph of this function looks like this. And if you factor the numerator, it can be written as x plus 7 times x minus 3 divided by x minus 3. So this function is undefined at 3. You can't put in 3 for x because you would get a division by 0 error. But as long as you put in any other number other than 3, the value you get out is x plus 7. It's the number you put in plus 7. So you're not allowed to put in 3, but for any other number, you get that number plus 7. So if you want to get out a number that's close to 10, you just have to put in a number that's close to 3. You can put in 2.9 and you get out 9.9. You can put in 2.999 and what you get out is that number plus 7, which would be 9.999. If you put in 3.1, you get 10.1. If you put in 3.0001, you get 10.0001. So it's kind of like our earlier dumb game. Whoever goes first, you plug in a number, you get out a value that's close to 10, but then the second player can plug in a number that's even closer to 3 and get out a value that's closer to 10. Okay, true or false? If A and B are any two real numbers, the absolute value of A times B is equal to the absolute value of A times the absolute value of B. Is that true or false? Well, it turns out that that is true. A and B could both be positive, they could both be negative, one could be positive and one could be negative, but you get the same final result if you multiply them first and then take the absolute value, or if you take each number's absolute value individually and then multiply those together. Well, what about this? Is it true or false that the absolute value of A plus B equals the absolute value of A plus the absolute value of B? Well, this is true only if those two numbers have the same sign. That is, if they're both positive or both negative. For example, the absolute value of -3 plus -4. We can add them together first and get -7, whose absolute value is 7. Or we can take absolute values first. Absolute value of -3 is 3. Absolute value of -4 is 4. 3 plus 4 is 7. But if they have opposite signs, the absolute value of A plus B is less than the absolute value of A plus the absolute value of B. So for example, if we have +3 and -4, if we add those together, we get -1, and then the absolute value of -1 would be 1. But if we took absolute values first, the absolute value of 3 is 3, the absolute value of -4 is 4, and 3 plus 4 is 7, and 1 is strictly less than 7. So what is always true is that the absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. And this fact is sometimes called the triangle inequality, because in 2 dimensions, if you took a step of whatever length in whatever direction, and then you took another step, the distance you are from your starting point is less than or equal to the length of your first step plus the length of your second step. That is, any one side of a triangle is less than or equal to the lengths of the other two sides added together. So basically, the shortest distance between 2 points is a straight line. But here we're working in one dimension, and so the only kind of steps you can take are forward and backward. So if I take a step in one direction and take another step in the same direction, how far have I gone? Well, it's the length of the first step plus the length of the second step. But if I take a step in one direction and then take a second step in the opposite direction, the distance that I am from my starting point is less than the length of the first step plus the length of the second step. So either way, it's less than or equal to the length of the first step plus the length of the second step. So we are going to be using this fact in something that's coming up. Now, if you saw my previous video where I introduced limits, one of the examples I showed was this one right here, that the limit as x approaches 3 of the function 2x squared minus 7x plus 3 over x minus 3 is 5. I showed that graphically. I showed it numerically. And I explained that that means that values of that function are close to 5 whenever x is close to, but not equal to, 3. That's what that means. So that means that I can get values of that function to be as close to 5 as I want. So when I say it's close to 5 and you say how close, I can say, well, how close do you want? I can get it as close as you want it. How close do you want? Do you want to be within 1/10 of 5? Do you want to be within 1/1000th of 5? Do you want to be within 1/100000th of 5? We can do that. Okay, say you do want to be within 1/100000th of 5. That means that the absolute value of 2x squared minus 7x plus 3 over x minus 3, the value of that function, minus 5, what we said the limit is, has to be less than 1/100000th. The distance or difference, how close these are, how close the value of the function is to 5, is very close. It's less than 1/100000th away. So how can we make sure that happens? Well, notice we can factor this numerator into 2x plus 1 times x minus 3. And as long as x is not equal to 3, that reduces to just 2x plus 1. Sorry, that should be a minus 1. That should be 2x minus 1, and then the x minus 3's cancel. And then, of course, 2x minus 1 minus 5 would be 2x minus 6. So we're saying that the absolute value of 2x minus 6 is less than 1/100000th. And we can factor that into the absolute value of 2, or just 2, times the absolute value of x minus 3 being less than 1/100000th. Then divide both sides of that inequality by 2, or multiply by 1/2, and the absolute value of x minus 3 is less than 1/2,000,000th, 1 over 2 million. So f of x, the value of this function, is guaranteed to be within 1/1,000,000th of the limit 5 whenever x, the number we put in for x, is within 1/2,000,000th of 3. So we've made precise what we mean when we say this function is close to the limit whenever the number we put in for x is close to 3. The absolute value of f of x minus 5 is less than 1/100000th whenever the absolute value of x minus 3 is less than 1/2,000,000th. Well, I got to qualify that a little. We said x cannot be equal to 3. So the distance between x and 3 has to be less than 1/2,000,000th, but it should be greater than 0. So that rules out plugging in 3 itself for x. So now let's look at that formal delta epsilon definition and see how that sort of matches what we've been talking about. Suppose f of x is a function that is defined for all x in some interval containing the number c, except possibly at c itself. So the function might or might not be defined right at that number. You might or might not be able to plug in that particular number, but it is defined for all the other x's that are close to that number. Maybe for all other x's, but at least for all other x's that are close to the number that x is approaching. The limit as x approaches c of f of x equals the number L if for every number epsilon greater than 0, there exists a number delta greater than 0, such that the absolute value of f of x minus L is less than epsilon whenever 0 is less than the absolute value of x minus c is less than delta. So here the epsilon and the delta represent positive numbers, probably very small positive numbers. It's just traditional in math to use epsilon to stand for a very small positive number. Like, well, in the example we were just looking at, the epsilon would have been 1/1,000,000. And if you want to get really mathematical and really concise, this definition can be written in all symbols. You can use symbols for all these words and write it like this. So this means for all, or for every epsilon greater than 0, there exists delta greater than 0, such that 0 less than the absolute value of x minus c less than delta implies that the absolute value of f of x minus L is less than epsilon. I won't work with it like that, but you might see it that way or write it that way yourself if you do lots of advanced high-level math, just to save you from writing the words over and over again. But in the example we were just looking at, the epsilon was the number 1/1,000,000. That was our example of an epsilon that was greater than 0, but it was still a very small number. And we found delta to be 1/2,000,000. So the epsilon is how close f of x is to the limit L, and the delta is how close x has to be to the number it's approaching, c. For a different epsilon, something other than 1/1,000,000th, we might need a different delta. But remember how we got this 1/2,000,000. We got it when we divided through by 2. So whatever number we have for epsilon, it would work to have delta being that number divided by 2. Delta can be epsilon divided by 2. So in general, delta depends on epsilon. Epsilon can be any number greater than 0, but then the value of delta is going to depend on what epsilon is. So let's look at this definition in action. Let's use it to prove, according to this definition, that the limit as x approaches 3 of x squared plus 2x minus 10 equals 5. You can probably see that that makes sense. If x is close to 3, then x squared is close to 9. 2 times x is close to 6. The whole thing is close to 9 plus 6 minus 10, which comes out to be 5. But how would you prove that rigorously from this definition? So here our f of x, our function, is x squared plus 2x minus 10. And our limit, our L, is 5. And our c is 3. So we need to show that for every number epsilon greater than 0, there exists a number delta greater than 0 such that the absolute value of x squared plus 2x minus 10 minus 5 is less than epsilon whenever 0 is less than the absolute value of x minus 3 is less than delta. So the plan, the thing we have to do, the plan of attack, is we have to figure out how the delta depends on the epsilon and show that for this choice of delta, 0 less than the absolute value of x minus 3 less than delta being true will logically imply or lead to the absolute value of x squared plus 2x plus 10 minus 5 being less than epsilon, that also must be true. Okay, so that's what we need to do. For any epsilon greater than 0, we need to find the delta greater than 0 that makes that work. So look at that expression, the absolute value of x squared plus 2x minus 10 minus 5. We can, of course, simplify that to the absolute value of x squared plus 2x minus 15. And then we can factor that into x minus 3 times x plus 5, both inside absolute value bars. Now that first factor, that x minus 3, is the one that's less than delta. So that part of it has to be less than whatever we choose for delta. If we said that delta was just plain epsilon itself, then that would guarantee that at least that part of it is less than epsilon, but then the whole thing would be less than epsilon times whatever the rest of it is. So what about that rest of it? What about the absolute value of x plus 5? Well, that would be equivalent to the absolute value of x minus 3 plus 8, because of course minus 3 plus 8 is equivalent to plus 5. And then by the triangle inequality, that would be less than or equal to the absolute value of x minus 3 plus the absolute value of 8. So we've got the absolute value of x minus 3, which is small. It's going to be less than whatever we choose for delta. So however small we make delta, that's how small the absolute value of x minus 3 is guaranteed to be. And if we knew that that was less than 1, then if we add 8 to it, we're going to get something that's going to be less than 9. So with that in mind, here's my choice of delta. I'm going to let delta be either epsilon over 9 or 1, whichever one of those is smaller. It's the minimum of those two things. That way it's going to be at least as small as both of them. So since we're talking about the absolute value of x minus 3 being less than delta, this would guarantee that the absolute value of x minus 3 is less than epsilon over 9, and also that the absolute value of x plus 5 is less than 1 plus 8, that is 9. And so when we multiply those two things together, we got one factor that's less than epsilon over 9 times another factor that's less than 9, and of course those things multiplied together would give you epsilon, so that proves that the whole thing is less than epsilon, which is what we needed to show. So that concludes the proof. Now, if you saw my video on finding limits analytically, or if you've studied this in calculus class, you've seen a bunch of limit laws or theorems about how limits work. The limit of a sum is the sum of the limits, and the limit of a product is the product of the limits, and things like that. And all of these can be proved using that delta epsilon definition. So let me just show you how that works on one of these. Let me show you the proof of the fact that the limit of the sum of two functions is the sum of their limits, provided both individual limits exist. So call those individual limits L and M. Let the limit as x approaches c of f of x be L, whatever that is, and the limit as x approaches c of g of x, we'll call that M. So we need to show that for any epsilon greater than 0, there exists delta greater than 0 such that the absolute value of f of x plus g of x minus L plus m is less than epsilon whenever 0 is less than the absolute value of x minus c is less than delta. We need to show that the value of f of x plus g of x is close to what we said its limit is, L plus m, whenever x is close to c. Well, take that expression, absolute value of f of x plus g of x minus the quantity L plus m, and rearrange it a bit. Put it so it's got f of x minus L plus g of x minus m. So same terms, but written in a different order. And then use the triangle inequality to separate that out into two separate absolute values. So we can say, according to the triangle inequality, that that's less than or equal to the absolute value of f of x minus L plus the absolute value of g of x minus m. Now, because the limit as x approaches c of f of x is L, we know that for any epsilon, and this is not necessarily the same epsilon that we were looking at earlier, so I'm calling this epsilon sub f, the epsilon just for the function f. We know that for any epsilon sub f greater than 0, there exists a number delta sub f greater than 0, such that the absolute value of f of x minus L is less than epsilon sub f whenever 0 is less than the absolute value of x minus c is less than delta sub f. So f of x is close to L whenever x is close to c. That's any number that we want to use for epsilon sub f, including for it to be that original epsilon divided by 2. Likewise, we know that for any epsilon sub g greater than 0, including if we pick epsilon sub g to also be the original epsilon over 2, there exists delta sub g greater than 0 such that the absolute value of g of x minus its limit m is less than that epsilon sub g, which we said was epsilon over 2, whenever 0 is less than the absolute value of x minus c is less than delta sub g. So for our big overall delta for the whole thing, we're going to just take the minimum of those two deltas, either delta sub f or delta sub g, whichever one of them is smaller. That way, it's guaranteed to be at least as small as both of them. That way, 0 being less than x minus c being less than delta means that it's less than both delta sub f and delta sub g. And that means that the absolute value of f of x minus L is guaranteed to be less than epsilon over 2, and that the absolute value of g of x minus m is also guaranteed to be less than epsilon over 2. And so when we add them together, we get something that's less than epsilon over 2 plus something else that's also less than epsilon over 2. So the total is less than epsilon. And that completes the proof. That's what we needed to show. So yeah, it does get a little complicated. That's why we don't normally use this definition to prove things about limits. We use it to prove these limit facts, or maybe we don't do it, but somebody has to. Some mathematician has to prove that, and then once it's proved, we can assume, oh, that's true, and we can use it to evaluate limits. By the way, if you've done any computer programming, this might be kind of analogous to how if you're writing a program, you can include some libraries that bring in some functions and procedures that have already been written for you, and you can just use those pre-written procedures to do things that you need your program to do without actually having to code them yourself or even worry about how they work. If you haven't done any computer programming, that analogy may not mean anything to you, but So let me just wrap up by saying that this delta epsilon definition for limits can be adapted in a fairly natural way to other kinds of limits. So if you go on to study things like one-sided limits, limits as x approaches infinity, limits of sequences, limits of functions of more than one variable like f of x and y, or limits of functions of complex variables, variables that can stand for complex numbers. This same definition with a little manipulation or tweaking works for those situations. So, like I said, this is something that you may or may not have any need to understand. So, I hope you found it at least a little interesting, a little helpful if you do need to understand it. So, that's kind of the theory behind the official formal mathematical definition of limits in calculus.